Okay, off we go. So, attendance quiz, attendance code, and all that. So a new subject today, we're going to talk about vector fields. This is a new, very important new construction. It's a new mathematical object that we have not talked about previously, and I would speculate you either haven't seen it previously or you haven't seen it previously in a math class. Most of you, all exceptions granted, of course. So, okay, now the definition of a vector field is that it is a function from Rn to Rn. This is not how we're going to be thinking about vector fields, at least in a physical and, sort of geometric, intuitive kind of way. But it is what it is. It's a function that has n inputs and n outputs. And by the way, to be clear, these numbers do have to be the same. So, okay, how do we think about it? What does it look like? How do we imagine it? And the idea is the input to the function, you're supposed to visualize as being a point in Rn. Just think of it as a location, specifically as a location, a point. And then you think of the output also in Rn, right? But you don't think of that as a point. You think of that as being a vector. And of course, how do we draw the vector? Well, vectors don't have a location. You can kind of draw them anywhere, I suppose. You're supposed to think of the vector as being something that is happening at that point. And just to most naturally, perhaps, make that clear, what we do is we draw the field vector, the output we call the field vector, with its tail at the input point. Okay, so you get pictures that look like these. You can see on the left I have a sampling of inputs and outputs, sampling of field vectors at their respective points in R2. And then likewise on the right here, sampling of points in R3. So now, of course, I can't draw all of them. If I drew all of the points and all the field vectors, the picture would just be solid pencil lead. Right? And you can't get anything from that. It's kind of like with level sets. You can't draw all the level sets. Then there's nothing to see. Right? So you draw a representative sampling and you find that compromise between, too much is confusing and too little is not enough information. Okay. All right. So now real quick, while we're looking at this picture, let's just talk about first reactions and tell you what comes to mind for me, right? Looking at this picture, practically leaps off the page at me. This is what I would draw if I was trying to represent the flow of a fluid. Now that's just me, right? Maybe different people have different images, contours in their minds. But if there were, let's say a river, let's look at this R2 picture here. If there were a river and if the flow, if the direction of the current at any given point was the vector that I have indicated here, well, you kind of get an idea of what the surface water of the river is doing. It's kind of flowing, kind of like that. It looks like the river is maybe taking a little bit of a right turn, something like that. Right? You get a nice natural picture. Okay. The one in R3 here, maybe you can't, I guess you could visualize this being water, but it might be more natural to visualize it as being air. Right? We live in a three-dimensional fluid of air, and so maybe this is some sort of an updraft. By the way, there's lots of different kinds of things that we could be representing the flow of, and we'll talk about some of these in a minute. I also like to think of this as being, hey, maybe there was a bunch of birds on the ground, and somebody scared the birds, right? And the birds fly up, and some of them fly over this way, but they generally kind of fly up. You can almost kind of imagine something like that, too, right? Okay. All right. Okay, more later on physical examples that are modeled by vector fields. Okay, so here are a couple of algebraic examples. Let's talk about this vector field right here. And keep in mind the input you imagine as being a point. The output, what we call the field vector, you represent with a vector with tail at said point. So there's an input and an output. And what you're going to notice, now you very quickly notice that this vector field is a constant, right? And so since it's a constant, no matter what input point you might be looking at, the field vector is always the same. And so it's pretty easy to draw a representative sample. And there you go. We have a nice communicative picture of this vector field. Is that cool? Is everybody happy? I will point out, I think this is worth observing, a lot of students at this point think, and sometimes even actively ask, hey, wait a minute, I thought if a function's constant, isn't the picture supposed to be like horizontal or something? Okay, now what's going on there is the students are conflating the graph construction with the kind of picture that we're looking at here. And it has to be noted, this is not a graph. It's absolutely not a graph. I mean, if nothing else, easy observation. There's 2 inputs and 2 outputs. If it were a graph, it'd be a 4-dimensional picture, not a graph. Right? So what is it? And I know it's getting a little out of hand, but this is the nature of multivariable calculus. This is our picture of a function number 5, right? So we have previously discussed graphs, level sets. We've talked about parametric curves. What we draw there, the actual parametric curve, is the image of the parameterization. That's 3. My little personal favorite, the literal picture where you draw the domain and the target separately, right? Those are all 4 previous pictures that we've talked about. This is none of them. Right? This is now a 5th kind of picture. And with that in mind, keep in mind, y'all heard me say it a million times, and we're probably about a third of the way through of the number of times you're going to hear me say this. But you got to keep the calculus of graphs separate in your mind from the calculus of level sets and separate from the blah, blah, blah. Right? So, yeah, there is a calculus of vector fields. And it is not at all the same as the calculus of graphs. Okay, so the idea that, I thought constants were supposed to be horizontal. No, that's graphs. This is not a graph. Does that make sense to everybody? So, new kind of picture, totally new kind of geometric intuition that you have to develop. Okay. All right, here's another example. Let's look at this one here. We'll play the usual process. The input point, think of this as being a point, wherever that might happen to be. The field vector, the output. Oh my gosh, look at that. The formula for the field vector is exactly the same as the input point that determines the field vector. XY goes to XY. Okay, wild. What does that look like? How do I draw that? Okay, so keep in mind the field vector I have to draw as a vector, not as a point. It's not a point. XY is a point. But points have position vectors. Right, so that point x comma y I can think of as being its position vector. And I can absolutely say that, hey, the field vector is the same as the position vector. Absolutely. It's just that that's not where we draw field vectors, right? The whole idea is we draw field vectors such that the tail is at the point. So this vector that I have in purple, this little arrow here, I'm just going to draw the same vector, same direction, same magnitude, but with the tail at the point. So I get that. And what you'll notice immediately then is that every one of these field vectors is pointing radially outward away from the origin, and such that its magnitude is the same as the distance from the point to the origin. And if you do that, if you do this kind of thing, but kind of, again, a representative sample of points in R2, then you get this picture right here. How we doing? Everybody follow that? Okay, good deal. So it's kind of weird. Constants don't look like we would expect constants maybe to look. And this one, XY goes to XY, you'd think it'd be a simpler picture, right? But it's a little funny looking. All right, the next one is a nice exercise. I'm going to outline how you're going to do this, but there is a critical step that I think is a very instructive and beneficial experience for you all to go through on your own. So again, as usual, the input point, we got some point in the domain. The output, we're supposed to think of the output as a vector with its tail at that input point. Okay, so what's the relationship between these? And there's a really nice relationship. It's going to come from imagining the input point, again, by its position vector. Let me do this with a pencil. I think this will look better. Pencil. We're going to imagine the position vector. And I claim if you take that position vector and do a quarter turn counterclockwise, that will give you, let's see here, that will give you something that's about like this. I claim that that is the field vector. But again, that's not where we draw field vectors. We draw field vectors with the tail at the point. All right, so from the fact that the input position vector rotates 90 degrees to get the output field vector, right? This is literally a 90-degree rotation. But you interpret that with, of course, the input position vector you got to view as a point, and the output field vector you got to draw with an arrow with its tail at that point, right? This is the resulting vector field, what that vector field looks like. So what I want to leave as an exercise for y'all, I think this is a very instructive exercise, is to confirm that what this F does, what it does to the input purple to get the output green, is literally a counterclockwise quarter turn. And here's how you're going to do it. You're going to recall that rotations are linear transformations. Linear transformations are matrices. Matrices are understood by their columns. The columns are the images of the standard basis vectors, all of that old linear algebra stuff, right, that we reviewed at the start of the course. And then just go through that process and write down, as by that process, what is the matrix that does a quarter turn counterclockwise rotation. And what you will find is that matrix multiplied by xy will give you negative y comma x. That's the missing piece of the puzzle that I'm leaving for y'all. So give that a shot. If you have trouble with it, you're not sure how to get started, if you don't remember what the deal is with matrices and columns and all of that, come talk to me in office hours. I'll be very happy to help. But I do think it's a good idea to give it a try on your own first. Okay. Is everybody okay? Everybody with me? Okay, here's a good one. This is actually a really important vector field for physics, which means it's a really important vector field for engineering. Y'all are, I understand, mostly engineers, all exceptions granted. This vector field right here. Now, it doesn't look particularly interesting when you write it like so. You see a cube in the denominator, and that always seemed kind of wrong to me somehow. But look at this quick little rewrite. Now, very easy to persuade yourself that nothing really happened there, right? But what's nice about this is you can see two things immediately. First of all, this is a radial unit vector. Wherever you might happen to be, that's a unit vector pointing radially outward from the origin. So the direction of this vector field is radial. And then the magnitude, you'll notice, is inverse square. So structurally, and of course now there's different constants depending on different physical scenarios, but as far as the sort of the structure of the formula, ignoring units, ignoring constants, that's what gravitational fields look like. It is also what electric fields look like. And again, pretty relevant, pretty natural in the physical world, right? Physics, kind of a big deal. Electric fields, certainly, right? They're going to be a big deal for anyone doing engineering. So, very important vector field to understand. There are some particularly curiously important features of this vector field that we're going to talk about when we get into chapters 6 and 7. And so let me just say more on that later. Really, really cool stuff. Okay. Everybody happy? All right, this next one's kind of just an observation. I claim we've already seen it. So we've talked about gradients. Y'all know what a gradient is. Right? We know how to compute gradients. Gradients, by the way, if you're looking at a graph, there it is again. You gotta think about what kind of pictures are you looking at, right? But when you're looking at a graph, which we are here, right? Graph. Gradients point uphill. There's that terminology, direction of steepest ascent. That's the fancy way to say it, but it means uphill. So, okay, that's old news. We already knew that. The modest observation I'm going to make here is that, that's actually a vector field. And again, we don't think about it in chapter 2. We don't think about it this way. But y'all know how to compute gradients, right? For this function, f. Plug that in for f, compute the gradient, you get this formula, 2x comma 2y. Back in chapter 2, all we were doing is thinking about 1 point at a time. And if you're only interested in 1 point at a time, you plug in what that 1 point is, and the gradient is just a single vector. But, okay, what if we're not interested in just 1 point at a time? What I have here is a formula that tells me whatever point you give me, here's the corresponding field vector. It's literally a vector field. Right, so gradients. Again, we didn't think of it that way back in chapter 2, but gradients are a wonderful example of vector fields. And by the way, also special vector fields, as it turns out. Very special vector fields. And again, many, many details that will come when we get to chapter 6 and 7. Okay. Now, real quick about terminology. Let me start with my preferred terminology. It's not the most common terminology, but this terminology I think makes the most sense. Here's what gradients do. Gradients, we just talked about. You give me a multivariable function, out comes a vector field. Comes as no surprise that when you take a gradient, the thing that comes out we refer to as the gradient. Well, right, of course, that's obvious. All right, now let's turn that around backwards, though. And in the spirit of, I'm sure y'all remember, when you're taking a derivative, what comes out is the derivative. What went in advance to make that, we call the antiderivative. Right? Y'all remember the term antiderivative? Right? Well, I propose that given a vector field, the function whose gradient is that vector field, we should call the anti-gradient of that vector field. I think that's very reasonable notation, terminology. In fact, this is so reasonable that even people who have not heard this term before will know what you mean. Right? It's self-explanatory terminology. So I think that's really, really nice. This is my preferred terminology. Now that said, it is not the most common terminology. The most common terminology is to refer to this as a potential function, which does not explain itself, right? This is not a self-explanatory term. So let me explain where it comes from. It comes from this little reality right here, and that is that there is this idea of potential energy. Right? So we've several examples of potential energy. If you haven't had a physics class, don't worry about it. But gravitational potential energy, right? If I lift my stylus up to here, now it has a lot of potential energy, and if I were to drop it, which I'm not going to, these are expensive. If I were to drop it, then by the time it gets down to here, it'd be moving really fast, and it would have kinetic energy. That potential energy turns into kinetic energy. Right, so anyway, that's what potential energy is. And potential energy relates to the corresponding forces. The weird thing is that given a force, the what we would by this terminology called the potential function is not potential energy. It's the negative of potential energy. I find that really uncomfortable. I mean, we're using the same word, potential, to describe something and its own negative. And does everybody see how that's super awkward? Right? Now, look, it's just a minus sign, right? And I think the physicist's take on this would be, it's just a minus sign. You knew what I meant. I mean, make a little note to yourself that when someone says potential function, don't forget the minus sign. I'm just like, okay, yeah, but why? Why are we painting ourselves into this weird corner where we are responsible to remember an extra minus sign? Let's just call it anti-gradient. Problem avoided. That's my personal preference. Now let me try to persuade you that this minus sign is there and is important. So again, most of y'all I think are familiar with the idea of potential energy, and I think you know that gravitational potential energy is proportional to z. It's proportional to altitude. Let's call that the z-axis. Well, the higher you go, the more potential energy you have. Literally, the formula for gravitational potential near the surface of the Earth is that it's a multiple of z. So the gradient is upward. But gravitational force is downward. That's the minus sign. Okay. So it's just a little awkward and annoying. I'm also going to make the observation that, look, there are plenty of situations where we're interested in functions and their corresponding gradients that have absolutely nothing to do with forces or potential energy or even physics. So having a terminology to apply to such a scenario that is narrowly, specifically about one kind of a physics interpretation. Again, I think that's too narrow, and I like the fact that the term anti-gradient is broadly natural and meaningful. Okay, so that's just my opinion. All right. Okay. So we've talked about forces. Right? We saw some examples where we were talking about flows of fluid. By the way, I like to think of this vector field here as, I think of this as the stirred pot. You imagine you're cooking some pasta, right? Whatever reason you stir the pot, and maybe you look at the pot from above, and this is the flow of the fluid on top of the pot of water. And again, we talked about how these kind of look like fluid flows. So yeah, sometimes vector fields represent forces, and sometimes they represent flows of fluids. Here's just a few more examples of kinds of fluids that you might want to model with a mathematical construction, and for which vector fields are the perfect mathematical tool. So in space, you can talk about how air flows. Right here we are in a three-dimensional room, and the AC is on, thankfully. And so the air is, I guess it's coming out of those holes and going into those holes, something like that. And there's a certain amount of air moving around the room. Well, wherever you are, whatever point you might be looking at, any point in space in the room here, the air has a corresponding velocity. At that point, it's moving with a certain velocity. At some other point over here, it's moving with a different velocity. For every point, there's an associated vector. That's a vector field. And then, a bunch of other examples. You can talk about how water flows around in the ocean. You can talk about how pollution flows around in the atmosphere, right? Not necessarily the same as how air flows around in the atmosphere. And blah, blah, blah. There's many other types of examples. The fun one, I think this is amusing. Animal migrations you can think of as a flow of a fluid. Now, I know you might not think of animals as being fluids. Let me try to change your mind on that. What is the stereotypical, the classic, the picture next to the word fluid in the dictionary? Water. What's water made out of? A bunch of little teeny tiny little particles. Very, very large number of teeny tiny itty bitty little particles. Okay. Let's talk about birds. And not on the scale of, what I see when I, look out the window, right? But on the scale of, globe size, right? Looking at, continents, etc. If we talk about birds migrating, on that scale, a particular, species of bird, well, there's a huge, huge number, millions, maybe billions of teeny tiny itty bitty little, kind of discrete little objects, kind of particles, that all kind of tend to flow roughly together. It's just like a fluid. Does that make sense to everybody? So it's kind of a funny way to think about animals, but I think it makes total sense. So, okay. All right. Okay, so there is a little calculation we're going to do. The point to this calculation is that the answer is going to be really interesting. So let me wait until the end to try to persuade you how important this is. That said, I do think this is a really natural question, right? Reasonable, natural question to ask. And so let's suppose you have some fluid flowing around. I'm going to represent the fluid flow by the field vectors give me the velocity of the fluid. And kind of like we were talking about with the air in this room, right? Wherever you might be looking, let's say right there, the air has a certain velocity. That's my vector field. And so, for example, at a point like that, maybe there's the fluid. And by the way, for the purposes of this calculation, I want this to be the simplest possible scenario. We'll talk about complicated variations of this a little bit later. So I want the field to be constant. Let's just keep it constant. And my little surface that we're going to talk about is flat and small. Right? This best case, simplest case scenarios. Okay, so we have a small flat area. Let's say like that. All right, so we've got a little area. By the way, I need to talk about not only how big that area is, I'm going to need to talk about how that area is oriented. How is it sitting in space? And we're going to describe that by way of a what we call a normal vector. Hopefully sounds familiar. N, y'all remember little n from equations of planes and stuff like that. And the idea is that if my hand represents how a piece of area is sitting in space, I can talk about how that area is how it's sitting in space if I simply understand what direction that normal vector is pointing. Tell me what the normal vector is doing, I understand then how that area is sitting in space. Is that cool? Okay. All right, so with all this set up, here's the reasonable question. Perfectly natural, reasonable question. We got all this fluid flowing. What's the, let's see here. Oh gosh, color choices. What's the flow rate? How much volume of air per unit time? Water, air, whatever it is. How much fluid in terms of volume of fluid per unit time is passing through that surface? It's like a perfectly reasonable question, right? Natural, obvious question. Okay, so here's the way I'm going to come at this. I think this is a reasonable first step. I'm going to say, look, in some amount of time, delta t, whatever amount of time delta t, I know the velocity and I know the time, and over that amount of time moving with that velocity, there's going to be a certain amount of displacement. The fluid will have moved in the direction of the flow by a certain amount. And that observed, I claim then that we can talk about the amount of volume in that amount of time, the amount of volume that has passed through that surface. Well, there it is. That's literally the pieces of fluid that flowed through that area in that amount of time, delta t. Is that cool? All right, so what is that volume? Well, volume is height times the area of the base. Right, high school geometry, right? Flashbacks, everybody good with that? Okay, height times the area of the base. Okay, wait a second. What is that height? This is the nice insight right here. This is arguably the sort of the big insight that height is the component. Let's see here, color choices. It's the component in that direction, the component in our normal direction of the displacement vector, D. Right, the displacement says how any little particular molecule of water moved. You start the clock, it started here and then it ended there. But that distance that it's traveled isn't the point. The point is what's the height of the parallelogram. I only need to know the component in that normal direction. Right, the extent to which the fluid is flowing parallel to the surface, who cares? I just want to know how thick is this parallelepiped. So that's a component. And of course, components we compute with dot products. In particular, components in the direction of a unit vector we compute with dot products. How are we doing? Again, that's kind of the nut of the argument right there. Is everybody happy with that? All right, it's kind of all over but the shouting at this point. Let's see here. Let me get rid of stuff we don't need. Let's see. Let's talk about that D vector. What is the displacement? Well, the displacement, keep in mind, we know the velocity is F. We know the amount of time that we're talking about is delta T. And displacement is literally velocity times time. And we're basically done here because the original question was to find flow rate, so volume per unit time. Well, there's volume and there's the amount of time that it took to produce that volume. And so volume per unit time is, is this right here. That's our flow rate. F dot N times the area. All right, everybody good? So it turns out that really the object of greater interest in this is not even the original question. The fact that this tells us volume per unit time of fluid is one of the big applications of this formula, this thing that was the answer to this question. But it turns out this thing is the more interesting object, and it has other interpretations, and it is very worth having a name and a notation. So the term is flux, right? Very common, very important construction. We're going to do a ton of stuff with flux, especially when we get into chapters 7, some in 6, a little bit in 6, but mostly in 7. And we're going to consider how to compute flux when the surface might not be flat, and if the vector field is not constant. And we got a lot of time, we got a lot of stuff to build up before we can do that. But it'll be a very important object of study. In physics, in E&M, one of the big important tools that you use a lot is flux of electric fields and magnetic fields. And it's got nothing to do with fluids. Right, so this construction right here, F dot N times area, is really the more important thing. Okay. All right, now here is a related exercise. I think this is a really good exercise. I'm going to walk you through sort of the approach that I want you to take. What if the vector field was not velocity? What if the vector field was density times velocity? And what if you're not interested in volume per unit time? What if you're interested in mass per unit time instead of volume per unit time? And by the way, it might not be density might not be mass per unit volume. It could be number of birds per cubic mile, or any of a number of milligrams of pollution per cubic yard or whatever. Right? Lots of different things it could be. So density times velocity, and we're interested in quantity per unit time instead of volume per unit time. And how would you do that? And it turns out the answer is exactly the same. Exactly the same formula. It's still F dot N times area. Now let me explain to you how you're going to do this, right? How you're going to show this. The way you're going to do it is you're going to recognize that the first thing you need to compute is the amount of, not volume, but mass that's flowing through. How are we going to compute mass? Well, you're just going to make the observation that mass is density times volume. We just stick on an extra factor of density there, which of course sticks on an extra factor of density right there, et cetera, et cetera. And then what I want to leave as an exercise for y'all is, then why does it disappear at the end? Why is it not part of the answer? And I'll give you a hint. There it is. I guess I'll just tell you. It's inside of the F vector. Right? F has density inside of it. So basically, you introduce density to get mass. The density carries all the way through the calculation, and it gets absorbed into the field. So, details, good to check. Be a fantastic exercise. I encourage you to try this. As always, if you get stuck, if you're not sure how to get started, whatever, right? Give it a little thought. I mean, make an honest effort of it, but if you really don't know what to do or you get stuck at some point, come talk to me. I'll be very happy to help. I'll totally walk you through it. Just come on into office hours. No problem. Okay. Alrighty. So before I go on to the next thing, let me just again talk about how important flux is. Flux, now we've seen two different applications of this. Flux, on the one hand, will tell you volume per unit time, that is, if the vector field represents velocity. Flux, the same formula, same formula, will also compute instead mass per unit time. That is, if your vector field is density times velocity. So it'll answer either one of these questions. Just set up your field appropriately. Flux gives you the answer you want. Alrighty. So this next page, it's another one of these. I hate having to skip over this, but there's some really, really beautiful math in here. I really like the ideas in here. I'm going to very broad brushstroke talk through the big strategy here. And by the way, what gets me happiest about this argument is that it addresses what would at first glance appear to be an extremely difficult situation, and it turns it into something that's actually pretty simple, right? And this is powerful stuff, right? So this is what I think defines a powerful idea. It's something that turns hard problems into easy problems, and it's pretty natural definition. Okay, so here's the hard problem. Let's suppose you have a light bulb. Okay, fine. Light bulbs emit little particles called photons that fly outward. They kind of fly outward, but kind of along with each other in some sense. Kind of like a fluid. Right? You can talk about the fluid of photons flying out of a light bulb. Fine and dandy, no problem. Here's the issue. The issue comes if you have two light bulbs. Right now, with that second light bulb, let's ask the reasonable question. Okay, now I've got photons flying around and stuff. Is that still a fluid? Well, the problem is, some of the photon at the given point, some of the photons are going that way, and some of the photons are going that way. What am I supposed to call the field vector at this point? I can't just pick between these two vectors, right? I mean, I guess I could add them, but why? What's aside from it's an answer, right? Why would it be natural to to just add those vectors. Why does that make sense? Okay? So this is a hard problem. By the way, this is only with 2 light bulbs. What if you had many light bulbs, or even worse? What if you had, such as in this example down here, a uniform ball of glowing gas, right? So you have this ball of gas, and it's not just glowing at the center. Every part in the entire interior of this ball is its own little teeny tiny itty bitty little light bulb. You've got infinitely many light bulbs. Oh my gosh, right? What do? How do we even make sense out of this as a vector field? And here's the really clever answer. I think this is a cool idea. What we did on the previous page, we said, suppose we know the vector field. And then we argued that we can then ask the flow rate. Right? Given a vector field, here's a formula that allows us to compute the flow rate. And we're just going to turn this around backwards. We're just going to say, well, look, empirically, I can measure flow rates. And if not empirically measure, maybe by some clever argument here or there, I can compute flow rates. Let's suppose we can compute flow rates. Which, by the way, you can in many circumstances. If you know all the flow rates for all of, a representative sample of surfaces, then you can ask, okay, what's the vector field that would compute flow rates correctly? That then is the vector field that represents the flow. So that's, roughly speaking, that's how we're going to answer it. That's how we have, if we had time, this is how we would have addressed this question. Anyway, I think it's a really nice idea. Wouldn't it be nice if we had all the time in the world we could go through this? It's a lovely argument. Oh well. By the way, if anyone's curious, you want to hear it, come on into office hours. I'd love to talk about it. Feel free. You don't have to. No expectations. You're not responsible for it, right? So you don't have to. But if anyone's curious. Okay, let's see here. Last thing in this section is, I think this is a pretty intuitively satisfying scenario I'm about to describe. And let's imagine, I like to have a metaphor to work with, so I'm going to imagine that we have a two-dimensional vector field, and I like to think of it as we've got some sort of a body of water, let's say a river, creek, stream, whatever. So we're looking at how the water is flowing on the surface of that river. And this is October, and the leaves are falling, and so appropriate to consider the question, if a leaf falls off of a tree and lands in the river, what's going to happen to that leaf? And I hope it's clear that if the water is flowing that way and the leaf lands here, the leaf will flow along with the water. Right? Perfectly natural? Anyone ever seen a leaf swim upstream? No, of course not. It's silly. It doesn't have a little motor on it or anything, right? It can't. It does what the water tells it to do. It can't do anything different. Okay, so here's how we're going to make this into equations. Imagine we're talking about the particle having, moving along some parametric path r of t, so position is a function of time, and keeping in mind that the water is flowing with a certain velocity. Let's say the vector field represents the velocity of the water. That's the velocity of the water. Okay, well, here's the observation that we just made. I'm going to say it in math now. Wrong color. Our leaf. If I want to ask what is the derivative of the leaf's position, and by the way, what is the derivative of the leaf's position? That's the velocity of the leaf. The velocity of the leaf is the velocity of the water. So let's pause on that for a moment. Well, yeah, of course it is. That's what leafs do. Leafs do exactly what the water tells them to do. Whatever velocity the water has, that's what the leaf is going to do. Now, we do have to recognize, though, that, here where the leaf fell, maybe the water has a certain velocity. Over here, way over here, the leaf's got nothing to do with what's happening over here. Way over here, the water might have a different velocity. I don't care. Right? What the water is doing somewhere where the leaf isn't is irrelevant. It's only where the leaf is. So the velocity at the point where the leaf is. So let me do this again with all of this having been noted. I just say it so it rolls off the tongue a little bit faster. The velocity of the leaf is the velocity of the water wherever the leaf is. That's all that says. And then let's recognize, of course, that the velocity of the water, that's what the vector field is. And so all together then we have that equation. And you'll notice that if the vector field is known, right, we have the actual vector field. What we have here is a differential equation because it's got a derivative in it. But it's a differential equation where what's on the left is a vector. What's on the right is a vector. Each one of these has, therefore, we were thinking 2 dimensions. Each one has 2 coordinates. What you have here is actually a system of differential equations. This is 2 differential equations together. You have to solve them simultaneously. And how to do that is a trick. It's not something that's immediately obvious, and it's not something that that is typically covered in intro calculus courses, or if you took Math219, it's possible you might have seen some solutions to those kinds of differential equations. If you took 218, I wouldn't think so, but I suppose that's possible too. But I wouldn't think so. Where you'll see how to solve these differential equations is Math353, which most of y'all are going to be taking in the spring. So, so y'all can look forward to that. What we're going to do here is just observe that there are certain scenarios where you can confirm solutions. I claim that if the vector field is this, now let's think this through, by the way. What is this vector field? Y'all recognize this formula? This is the stirred pot, right? This is the vector field that's kind of going around like this. Now, before we go on with the math, if you have a stirred pot, and if you drop an oregano leaf, right, preparation to make your pasta, right, that oregano leaf is going to go around in a circle, isn't it? Right? Seems like it might be plausible then that maybe this, y'all recognize, of course, as a parametrized circle, maybe this would be the path that it would follow. Maybe this then would satisfy the differential equation. And in fact, if you plug this into there and there, and using as your vector field, using this, you compute the left side of the equation, you compute the right side of the equation, and it works. So we don't know how to solve the differential equation, but we do know how to confirm a solution. And that is a solution to that differential equation. Yes?
Are you able to combine different vector fields? Like, say, the path of the leaf depends on both the flow of the water and the wind?
Let me think about that. Sure. We could do something like that. What you'd need to have some knowledge of, okay, how much does the wind affect the motion and how much does the water affect the motion, and then you could, as you say, kind of maybe combine them to get a sort of a combined vector field. I can see something like that. Totally. Yep. Absolutely. That's I'm going to call that somebody else's problem. I'm going to call that a physicist's problem, or maybe an engineer's problem. But yeah, absolutely. Whatever the combined, this is what the fluid is doing overall, all things considered. makes the differential equation, and that's what we start to care. Okay, let's see here. We're about out of time. Let me just give you one last super quick thing. Please don't make the mistake of picking your favorite metaphor for vector fields. A lot of students make this mistake of saying, you know what, fluids just don't make sense to me. I'm a forces kind of person. I'm going to imagine everything in terms of forces. Not going to work. We're going to be doing a lot of stuff with fluids. You've got to get cozy with the idea of fluids being represented by vector fields. And vice versa. If the fluids seems natural to you and forces are weird and mysterious and I don't get that, well, you're going to have to get comfortable with it because there's stuff we're going to be doing that is unavoidably about forces. So make sure to get comfortable with both of these. Y'all have a good rest of your Wednesday. See you later.
Ha ha ha!